Hi, my name is Jim, and today's topic is decibels, which is the de facto standard for signal level energy measurements in just about everywhere. So I'm going to start with a little review of the linear and log domain. Now this comes about in the 20s when the Bell Laboratories determined that making power level measurements didn't correspond readily with people's ability to hear, and the rule of thumb was that if there was a conductor for an orchestra and he wanted the violin section to be twice as loud, he would have to hire 4 times as many violinists to make that double in apparent listening ability to be twice as loud. So there's definitely a nonlinear relationship between acoustical power and what human beings perceive to be loudness. So we're going to start with a comparison between the linear domain and the log domain. And in the linear domain I have listed these mathematical operations and also their equivalent in the log domain. Now, before we get into this, you might be thinking, with calculators today, why do we need the log domain? And to an extent that's true. However, in the industry we're going to be talking about decibels everywhere. Power levels sometimes don't even come up. And when I say power level, I'm referring to the power in watts or milliwatts or microwatts or whatever. So in the linear domain, multiplication is represented in the log domain by adding. And it's very important to remember this. Division is represented by subtracting, exponentiation by multiplying, and finally, if you take the root of a number, that would be dividing. So taking some very general examples here, and it would probably be a good thing if you followed along with a calculator. And this is log base 10, not the linear log or the natural log ln. So what we want to do is multiply in the log domain. So we're going to be adding, basically. In the linear domain we're multiplying 3 times 4. So on our calculators, if we take the log of 3, that comes out to be 0.477, and likewise the log of 4 comes out to be this number. And then to multiply them, all we do is add them together, which gives us 1.079 here. And now to get it back in the linear domain, we have to take the inverse log of it. Now some calculators have log -1 as a key, and other calculators have 10 raised to the x is the key that will take the inverse log of a number. So depending upon what you have, that would be what you do. Now my calculator uses this technique, so I'll be moving away from log -1 for the inverse log operator. And anyway, taking 10 and raising it to the 1.079 power yields an answer of 12, which is correct, 11.999. So we can see that the multiplication kind of makes sense by adding. And let's take a look at division, and what we want to do is take 20 and divide it by 5 and get 4. So we'll do the same thing as we did before. We'll take the log of 20, and then we'll take the log of what we're dividing by 5, which gives these two numbers respectively. And since subtraction in the log domain is equal to division in the linear domain, we'll just subtract these two numbers, giving us 0.602. And then once again, taking the inverse log of that yields the correct answer of 4, written as 3.999. So next example will be exponentiation in the log domain, and our example here will be 5 squared is 25. So if we take the log of 5, we end up with this number, and we're going to multiply that number by 2. And 2 is the power that 5 is being raised to. It could also be, say, 5 to the 3rd or 5 to the 2.5 or whatever. It's simply multiplied by the log of the number, and what that gives us is 1.398. Once again, taking the inverse log of this will give us 25 is an answer for 5 squared. So if we elect to look at 5 cubed, for the heck of it, we see 5 to the third power is 125, and now we get 3 times the log of 5, so that would be this guy, and the 3 here would be this guy. Ends up with a number 2.097, and then taking the inverse log of that gives the correct answer of 125. Finally, taking the root of a number, say we take the square root of 25, and it's kind of important here for demonstration purposes that I put the 2. Else when we get down into calculations you won't know where it comes from, and square root of 25 is 5. So first what I'm going to do is take the log of 25, which yields this number, and then I'm going to simply take it and divide it by 2, and this is where the 2 comes from, giving me this number here, and then taking the inverse log of it produces the correct answer of 5. Next, suppose we wanted to take the cube root of a number, in this case be 27. So here's our guy here, and the answer to that would be 3. So if we take the log of 27, gives us this number, and then all we do is divide that by 3, giving us 0.477, and then taking the inverse log 10 raised to the 0.477 power ends up giving us 3, which is the correct answer. So that's basically an overview of logs in general. And now we'll get down into the electrical component of this, and the unit that was decided upon for decibels actually was the Bell, B-E-L, and the commission named the unit in honor of Alexander Graham Bell. It's spelled with one L, and it was found to be too large, and therefore we use deci, meaning 1/10 of a bell. And where you've seen this before is that 1 joule equals a watt second. That's 1 watt times 1 second. And on the electric meters of your house, what your energy measurement is, and the joule is a unit of energy measurement, we have 1,000 watts times hours. So here's our unit of time, and here's our unit of power. So this unit of measurement would be in a kWh. Now the reason that electric meters use kilowatt hours is that joules would produce an awfully large number, where 1,000 watt hours is a more reasonable number. So in that way, it's similar to using 1/10 of a bell. It gives us a reasonable number, and realistically what it does is it avoids a leading decimal point. So if we take an amplifier here, say this guy, and this is a symbol for an antenna, and an example of this may be a taxicab base transmitter. We have 200 watts out, which is a reasonable value fitting the antenna, and the power amplifier for that stage is 15 watts in. Now you may be thinking, wherever did I see an amplifier with an input power specified? By 50 watt per channel stereo, that's certainly the output power, and millivolts comes off CD player or MP3 device or whatever. You don't typically see this, but in the RF world, when you're dealing with powers like this, the amplifying device, be that solid state or in cases, even today, vacuum tubes do require power input. It doesn't just come free inside of this. So if we wanted to find the gain of this in decibels, and remember that decibels is a ratio, it doesn't have a unit associated with it, our formula would be decibels equals 10, and the 10 comes from the deci part of decibels, times the log of the output power, 200 watts, divided by the input power, which in this example is 15 watts. And that'll give us a gain in decibels of 11.25. Again, dimensionless. Now if we look at this, we have watts divided by watts. So the units of watt cancel out, and it's just in the linear domain the ratio of 200 divided by 15. So it's very important when you do a log operation that that number be dimensionless. You can't have a unit in a log operation. So let's move along a little bit further with an example here, and this is our taxi cab transmitter before, and here's our antenna, and antennas don't know if they're transmit or receive. They don't have a concept of direction. And what happens is that as this is transmitting, say, the dispatcher's voice, it's also receiving signals from other radio stations, TV stations, cellular towers, whatever. And it's feeding that down back into the amplifier, and what that can do is cause this to pull and shift a little bit. Now that's kind of bad. The FCC doesn't like it because if this shifts around, it could be out of band and interfere with some other transmission, say air traffic control. Not good. Fire base station transmitters and so on and so forth. So a device is put in here called an isolator, which lets power move in this direction but absorbs power coming down from the antenna. And like anything, it's not for free. It has an insertion loss, and I've shown this insertion loss here of being 200 watts in and getting 160 watts out. So let's find the gain of this system with the isolator, and we would do that the same way as we did before. dB gain equals 10 times the log of power out over power in, 10 times the log of 160 there, a little smeared up, divided by 200, and that gives us a gain of negative 0.969. So when we have a negative gain, that means that the power output is less than the power input. We could also say that the gain is equal to negative 0.969, or I could say that the loss is equal to positive 0.969. So loss implies a negative on the gain. This is similar to ripple rejection ratio, which on data sheets for voltage regulators is given as a positive number, like perhaps 70 dB. When you enter that into a calculation, say to find the ripple voltage coming out of a regulator, you would enter that as negative 70. Now the word ripple rejection ratio infers that it's negative, just like the word loss infers that it's negative. So the linear gain, if you will, of this system here then would be 0.8, which is less than unity. So suppose that we have a system here with 5.2 watts in and 5.2 watts out, and this might be a buffer amplifier, and we wanted to find the gain in dB. Is we would do the same operation, end up taking the log of 1 and ending with 0 dB. Now what you have to remember is 0 dB does not mean that there's nothing there. What it does mean is that the gain is unity. The linear gain is equal to 1. So 0 dB represents a gain of 1. Now, suppose we had a power amplifier before, and this is for power. When we get into voltage and current, we have to do something a little bit different. So everything we're doing right now is for power, and suppose we know that an amplifier has a power gain of 20 dB, and that the output power is 50 watts, and the question then becomes well, what's the input power? How do we solve that? And what we see is that the input power is one of the arguments of the log operator, and the name of the game is to isolate the variable as standard procedure. So we'll just populate the equation here. We have 20 dB, that would be the gain, 10 times the log of power output, which would be 50 watts divided by power input. So we'll start by getting the log operator all by itself, and to do that we'll divide both sides by 10, giving us 2 equals the log of our 50 watt output power divided by our input power, which we want to find. Now we're going to take the inverse log of both sides, and I've verbosely written this. So log minus 1 of 2, and this is convenient relative to 10 raised to the power, is equal to the inverse log of the log of 50 over Pn. Now we don't have to write it this way, I'm just doing that to kind of be sure that everybody understands that we're going to end up with the ratio without a log operator over on the right hand side of the equal sign. So in doing that, if we take the inverse log of 2, is we get 10 squared equals 50 watts divided by Pn. Squaring 10 gives us 100, and then what you're wanting to do is get the power in all by itself, and in so doing we see that the power in is equal to 0.5 watts. So we can find P out or P in, and what we have to do is to get that as a ratio without being a component of the log operator. And if we wanted to check this, dV, which we expect to be 20, would be equal to 10 times the log of 50 over 0.5 watts equals 20 dV. Now what you have to be careful of is I could also express this 0.5 watts as 500 milliwatts. So remember, the units have to cancel. So either you convert the numerator into milliwatts or the denominator into watts, and that's the number that you'll be dividing. So for a kind of conclusion on this is I've got the linear domain here and the log domain, and a gain in the linear domain of 1 would equal 0 dB in the log domain, and a gain greater than 1 in the linear domain, like gain of 2 or 3 or whatever, would be a positive number in the log domain, and a gain less than 1 in the linear domain will produce a negative number in the log domain, centered on 0. So that's kind of the overall scheme of things, and you have to remember this here: 0 dB gain is equal to unity in the linear domain. Very important. Alright, we're going to move on into a derivative of power gain here, and dB is a ratio. It's dimensionless. It's volts or watts over watts, and if we wanted to express something as a power in the log domain, one of the things we might use, very, very common, is dBm. And as we go on, we're going to see different postfixes on dB, which mean different things. So dBm is defined in the following way: 0 dBm is equal to 10 times the log of the power in watts divided by the reference level, and this never changes for dBm. This guy here is always 1 milliwatt. So for an example, suppose we wanted to find the transmit power of a microwave system if the actual radiated power is 1 watt, and we want to measure that in dBm. And understand that many test sets measure power in dBm, and we'll be seeing that in a little bit coming up. So to find that, it would just be 10 times the log of 1 watt over 1 milliwatt equals 10 times the log of 1,000, and the log of 1,000 is 3, so 10 times 3 would be 30, which would be 30 dBm. So if we connected a test meter to this microwave transmitter, it would be measuring about 30 dBm. Now suppose we have the opposite problem. Find the power in watts of a microwave transmitter if it produces an output of plus 27 dBm. So in this particular case, we want to know what the actual power is in watts. So this is our general equation that we'd be setting up as before, and now we just populate this here. We have 27 times 10 times the log of P, the guy we want, in watts, divided by our reference, which is 1 milliwatt. And dividing both sides by 10 gives us 2.7 equals the log of P over our reference, 1 milliwatt. And that would be this guy here, and then taking the we're raising 10 to the 2.7 power would give us 501.2 equals our power divided by 1 milliwatt, and then it's very simple to find out what the power would be, and that comes out to be 0.5 watts. So like determining the gain is just a matter of manipulating and getting the unknown all by itself. Now what you might notice here is that this here had a launch power of 1 watt, and this guy here is down 3 dB. This is 30 dBm here, and this is 27, and the power is a half a watt. So every 3 dB means that you're either going to double the power if it's a positive 3 dB, or reduce the power by 50% if it's a negative 3 dB. One last example here, and determine the optic receive power in dBm. Now this is what technicians use to do this. So they have fiber optic transmitter here, and the launch power of this is 2.5 dBm, which it's an infrared laser doing this for long distance work. That would be single mode, but we won't get into that now. And our fiber optic cable going from this place to that place has a loss of 15 dB, we'll say, and technician needs to verify the loss over here. Now, keep in mind that this may have many splices in it, sometimes in manholes. So it's always good to know this before you connect it to a fiber optic receiver, because the receiver has a window of if the power is too high, it won't function well, and if the power is too low, it won't function well. So it has to be within that window, and that's why somebody would want to measure that and make sure that it's a good system. So the math on this, and this is where I think decibels will really be explained as being useful, is that our 2.5 dBm, which is a power level, minus 15 dB, which is a ratio, gives us negative 12.5 dBm, which is a power level. And that would be what a test set connected to this location should measure. Now, if the fiber optic receiver has a rating of negative 10 dBm to negative 25 dBm as its acceptable operating input power level, we're good to go. Technician would disconnect this from the power set, connect it down to the fiber optic receiver, and then they'd run some type of tests on it, like bit error rate and things like that. So, fiber optic cable loss here, and that is a loss, is going to be 15 dB, and I'm expressing that as a loss, not as a gain of being negative 15 dB. And that's the way in the fiber optics world, which is, well, everywhere, that technicians go about making power measurements and installing and testing circuits. So that'll do it for our introduction to decibels, and we need to revisit the topic dealing with voltage and current. Thanks for watching.